Fairly recently we realized that basically all stars host planetary systems. But we also discovered that our own solar system is quite weird compared to the rest. In fact, we've never seen another system quite like ours. So either we are extremely rare or we're about to discover countless other solar system twins in the next big data drop from Gaia. Could go either way. But the answer holds deep implications for the rarity of life in the universe. There are lots of reasons to search for planets around other stars, known as exoplanets. A major one is to find other places in the universe that might harbor life. Currently we only know of one such planet, and that is Earth. Naturally, we get particularly excited when we find Earth-mass planets at the right distance from their star to sustain liquid water, which is critical for life as we know it. We've found lots of those habitable worlds. But we also don't know what factors are truly critical for the initial development of life. Maybe star type. We get even more excited if that Earth mass is at the right distance from a Sun-type star. We found a few of those too, and we can infer that there are lots more out there. But is that it? There may be other astronomical factors. For example, it's been speculated that Jupiter was critical for the development of life on Earth because it protected us from excessive bombardment by comets and similar debris. So how many Sun-like stars have we actually discovered that are confirmed to have both habitable Earth-like planets and also more distant Jupiter-like planets? 0. Not a single one. There's some evidence that such systems are actually truly rare. But it's also true that our current methods are just not good at finding these sorts of systems. Fortunately, new work based on the Gaia satellite is about to fix that. And hopefully it will tell us how common or exceedingly rare a solar system like ours really is. Before we get to how we might figure out the true uniqueness of our solar system, let's do a whirlwind tour through the history of exoplanet discovery. That will give us a good understanding of the methods we're going to need to search for our solar system's twins. Planets are not easy to see. They're small and dim compared to their parent stars. We've managed to snap pictures of a few with sophisticated starlight blocking and image analysis technology. But that's relatively recent and very difficult, meaning it is no good for taking a large-scale census of planetary systems. For that we need to use indirect methods that rely on the near-invisible planet's influence on its home star. In 1992, radio astronomers announced the discovery of the first 2 exoplanets. They orbit a millisecond pulsar, an ultra-compact stellar carcass that rotates 160 times a second. The crazy magnetic fields of this neutron star channel beams of high-energy particles whose radiation sweeps past the Earth with a regularity exceeding the best atomic clock. In this one pulsar, a modulation in the timing of the pulse revealed the gravitational tug of 2 planets, with a third following soon after. Well, that's cool, but definitely not solar system-like in any respect. The next confirmed exoplanets all came from the radial velocity or Doppler method. Planets don't really orbit stars. Stars and planets orbit their mutual center of mass, their barycenter, which is always close to and often inside the star because the star's mass is so much larger than the planet. But that means stars do wobble in response to their planets. That wobble can be seen as a tiny change in the star's velocity, in turn seen through Doppler shift. That's the tiny stretching or squishing of the light wavelength depending on whether it's moving away from or towards us. A few planets were found this way through the 90s. All of them giant and with small orbits because those are what the Doppler method is most sensitive to. The exoplanet gold rush really only started in the new millennium with tens of new planets a year. Most of these were via the radial velocity method thanks to new high-resolution spectrometers like Keck-Hires in Hawaii and HARPS at the European La Silla Observatory in Chile. Smaller and less hot planets were found, but still nothing like the Earth. Most of these were gas giants orbiting close to their star. I remember a time in the 90s when most planetary systems we knew of consisted of inner solar systems filled with gas giants. We had no idea if other Earth-like planets even existed. But the 2009 launch of the Kepler Space Telescope changed everything. The spacecraft had one job: to stare at a tiny patch just 1/400th of the sky and make precision measurements of the brightness of the 150,000 stars in its view. Tiny repeating changes in those brightnesses revealed miniature eclipses, or occultations, as exoplanets passed in front of their home star. This only worked for planetary systems with convenient alignments, but there were enough of those. By the mid-2010s we were averaging hundreds of new exoplanets each year. And this method was finally sensitive to Earth analogs. In principle anyway. We found several Earthish-sized planets in their stars' habitable zones. Most of these are around red dwarf stars. But also a handful around stars that are more like the Sun. Extrapolating from Kepler's discoveries and taking account of planets that Kepler probably missed, astronomers inferred that there are something like 11 billion Earth-like planets around Sun-like stars in the Milky Way alone. This huge number of Earth-Sun analogs is promising. But there's a catch. The majority of planetary systems catalogued by Kepler and other transit and Doppler surveys seem to look nothing like our solar system. Planets of a given system have a surprising tendency to be all roughly the same size. Maybe you remember the TRAPPIST-1 system with its string of 7 roughly Earth-mass planets orbiting close around a red dwarf. More common are chains of super-Earths or mini-Neptunes. The thing we don't tend to find is a chain of terrestrial planets in the inner system followed by a chain of gas giants in the outer. The term peas in a pod describes this new picture in which planetary systems tend to have similar mass planets. If that's how such systems tend to form usually, then it raises big questions about why our solar system didn't form that way. There are solid hypotheses for this. The most prominent being the Grand Tack hypothesis. This suggests that Jupiter migrated into the inner solar system, disrupting the larger worlds that were developing there before retreating to the outer solar system again. The inner system then had to pull itself together from the depleted remnants of Jupiter's rampage. If this event resulted from some unusual gravitational interaction, say with a passing star, then it might mean our planetary configuration is pretty rare. But we just don't know how rare. The main reason for that is a bit surprising. Jupiter-like worlds and Jupiter-like orbits are actually hard to confirm from past surveys despite being so much more massive than any terrestrial planet. The main challenge is the length of the year of such an outer solar system body. 12 years in the case of Jupiter. Now the Doppler method can identify a Jupiter-like companion from the wobble it induces in its star. It even measures the properties of that orbit without having to observe a full orbit. However, the Doppler method is not well suited to the initial discovery of exoplanets. It can't track many thousands of stars at once in order to identify candidates. Now the transit method can do that. For example, Kepler. But that method takes a lot longer to identify an exoplanet. Each transit is seen as a little dip in the star's light. We need to clock at least 3 of those dips to even recognize a candidate exoplanet from the regular spacing of the dips. The Kepler mission has no more than 4 years of observations on any given star. So it could potentially have flagged an exo-Mars but definitely not an exo-Jupiter. Now we could keep doing planetary transit observations until we have enough of a temporal basis and enough stars to see long-period gas giants. And the TESS satellite has now picked up where Kepler left off. But it'll still take decades to confirm an exo-Jupiter. Fortunately, we can do this a lot quicker by switching to yet another completely different method. As I mentioned, close planets cause their stars to wobble fast, which is good for the Doppler method. But more distant planets cause their stars to wobble far. And this raises an intriguing possibility. If we could actually see the stars moving, not just by their Doppler shifts but actual changes in position, then we might be able to catch these large orbit exoplanets. To do this, we would need incredibly precise measurements of a star's position. That's why we call this approach the astrometry method, where astrometry is just the science of precision measurement of celestial positions. So let's see how that could work. Both star and planet orbit their mutual center of mass or barycenter. The location of the barycenter depends only on the masses of both objects and their separation. It's always closest to the star, but the distance of the barycenter from the center of the star is proportional to 2 things: the relative mass of the planet and the distance of the star to the planet. Planets with larger orbits actually pull the barycenter further from the star than those with smaller orbits. And that's perfect because it makes this astrometry method more sensitive to large orbits, whereas both the radial velocity and transit methods are better for small orbits. And that's exactly what we want for finding exojupiters. We do still have the problem that these sorts of wide-orbit exoplanets also have long orbital periods. But with the astrometry method, we actually see the orbit playing out and don't have to wait even a full exo-year to start to characterize the orbital parameters. Finally, astrometry can detect planetary systems with any alignment, whereas the transit method only catches those that happen to be conveniently oriented so as to produce said transits. And even the Doppler method is insensitive to systems flat against the plane of the sky. Okay, so now we have a third method for finding exoplanets that seems to shore up some of the weaknesses of the other two. So what have we done with it? Well, this is exactly how astronomers first confirmed that Sirius, the brightest star in the night sky, has a faint white dwarf companion named Sirius B. That was way back in 1844. Plenty of other binary stellar companions have been found this way, including things like companion black holes and neutron stars. But detecting an actual exoplanet this way is much harder due to the teeniness of the star's wobble and the extreme resolution required to see that wobble. It wasn't until 2010 that we detected our first exoplanet via astrometry. But at that point Kepler was in full swing and just way more productive. What we needed was a dedicated astrometry satellite. Enter Gaia. Gaia was launched in 2013 and took data until March of this year, over which time it scanned the entire sky over and over to make a census of 1 billion stars in the Milky Way. The main superpower of Gaia is precision astrometry. It does this in a cool way. Gaia has 2 telescopes on a spinning platform and achieves precise position measurements by converting the problem into a precise measurement of the time the star crosses through the fields of view of the 2 telescopes. By combining 50 to 75 observations, Gaia can achieve a position resolution of roughly the angular size of a US quarter on the Moon. So Gaia's primary goal was to measure stellar parallax. That's the apparent shift in a star's position as Earth orbits the Sun. Gaia has enabled astronomers to calculate distances to 1.3 billion stars across the Milky Way. And combining this with the velocities also measured for many of those stars, Gaia has given us this incredible dynamical map of a good chunk of the galaxy. But if Gaia can see a star's apparent wobble due to parallax, it should also be able to see an actual wobble due to the pull of the star's own planets. The first Gaia exoplanets found using astrometry are Gaia 4b and 5b. Both superjupiters with 12 and 21 times the mass of Jupiter respectively. Both orbiting nearby low-mass stars. It was a painstaking task to sift these out of Gaia's third data release in 2023. First, astronomers had to identify wobble consistent with exoplanets and then rule out other causes and then follow up with radial velocity measurements to confirm. But Gaia 4b and Gaia 5b are definitely there. These objects are unusual because they're superjupiters orbiting stars that are smaller and less massive than the Sun. This combination of giant planet and small star was thought to be extremely rare, so we've already learned something new here. But then again, the wide orbits of these guys make them hard to see by other methods, so we never really knew that much about such systems in the first place. What we do now know is that Gaia can spot gas giants far from their stars. Gaia 4b and 5b have proved that. And in astronomy, where there's one, there are many. These planets mean there is a whole population of undiscovered planets hiding in the Gaia data waiting to be discovered. And that's going to happen following Gaia's Data Release 4 in December 2026. The Gaia DR4 will be different because it will include for the first time Gaia's time series measurements of stars' positions on the sky rather than just the parallaxes. DR4 will also span 5.5 years. About twice as long as DR3. This enables the detection of planets more distant from their stars because these take years to complete an orbit. Candidate exoplanets will be followed up with radial velocity and Doppler observations. These will confirm cases of interest and better measure the properties of the planets. But without Gaia, we wouldn't even know where to start looking in the first place. Okay, so how many exoplanets do we expect Gaia to find? Well, we talked to the astrophysicists who figured that out. Caleb Lammers and Josh Wynn, who recently published a study on exactly this subject. Based on simulated Gaia data, they predict that Data Release 4 will lead to 7,500 exoplanet detections, give or take a couple thousand. This is likely to more than double the number of known exoplanets, which currently stands at about 6,000 confirmed, around half of which are from Kepler. Gaia DR4 will include only half of the data that the Gaia Space Telescope has collected. The full dataset DR5 will include astrometric measurements spanning 10.5 years and will be released in the early 2030s. The number of exoplanets will then explode even over the DR4 figure. There are 2 main reasons for this. The longer time span of observations makes Gaia sensitive to planets with longer orbital periods. So just more planets? Also, these longer orbital periods correspond to physically larger orbits, and that means larger stellar wobbles. And the larger the wobble, the further away it can be detected by Gaia, making the mission sensitive over a larger volume of space. Lammers and Wynn predict that DR5 will include a staggering 120,000 planet detections, give or take. That's a 20-fold increase on current exoplanet numbers. But will we detect our solar system or one like it? Gaia will be sensitive to Jupiter-like worlds and those larger so-called super-Jupiters with orbits within 1 to 5 times the Earth-Sun distance or astronomical units. Jupiter itself is at 5.0, so Gaia should be able to spot a Jupiter analog. It won't be sensitive enough to detect the wobble due to Earth-like planets, but that's fine because TESS will observe a chunk of Gaia's systems to get the inner systems of those. This combination of astrometric detections from Gaia and transit discoveries from Kepler and TESS will give us something close to a comprehensive census of possible planetary systems. That's going to allow us to really refine our understanding of the formation and evolution of these systems. In the case of the gas giants, for example, the ones that Gaia will discover, we may learn whether they form more like terrestrial planets from small bits clumping together or more like stars with a large cloud collapsing. But it's the combined knowledge from Gaia plus TESS that will teach us the most about our own solar system. It may be that we even find a true solar system analog out there with an exo-Earth discovered by transit and an exo-Jupiter in the same system found through the wobble it produces. And if we don't find such a system, or find very few, that will confirm what some already suspect: that our solar system is really quite a rare beast capable of nurturing a uniquely habitable world amid rich planetary diversity that fills our galactic spacetime.